So we're going to be analyzing at least 2 samples, maybe more, depends on how much time you have. The first sample we're going to analyze is what's called the known. The known solution has every single one of these. And so you should be testing positive for every single one of these. If you aren't, then something went wrong. The second solution that you're going to test is the unknown. The unknown is going to have a select number of these. And so sometimes color can help you identify, if your unknown is totally colorless, then you probably can eliminate some of these. But it's tricky because sometimes it's dilute, so the color doesn't really stand out. So you might have some, but it's just in low concentration. So anyway, for the known solution, you can either work alone, independently, or you can work with a partner. But for the unknown, you have to work individually. And then for the unknown, for the known, you can have your lab manual. The lab manual would just be this handout. You could have the handout and your notebook. For the unknown, you're going to do it strictly from your notebook. What types of observations do you need to take in your notebook? The types of observations you need to take in your notebook are enough observations so that you can repeat the experiment. So let's see if you could repeat the experiment based on your observations that you took for your known, without having to go back to the procedure and look at the procedure to figure out what you were doing. The observations should be adequate enough to do it. Let's see. Make sure this is still recording. Okay, so let's take a quick rundown of some of the chemicals we're using. 6 molar H2SO4 sulfuric acid causes some burns, But when we compare 6 molar versus 18 molar causes severe burns. And this would be equivalent to, let's say, a second or burn if you spilled this on your skin. So don't, actually, if you're dealing with 18 molar, treat that. This is as concentrated as you can get, for sulfuric acid. And so it can't get more concentrated than this. And so this is what we call concentrated sulfuric acid. This is what we call dilute sulfuric acid. But dilute sulfuric acid can still cause burns. And so avoid contact with, especially with the 18 molar H2SO4. HCl, we're using dilute and concentrated. Concentrated HCl is 12 molar. 12 molar gives off lots of fumes. It's fuming pretty much. And so if you put like 12 molar under your nose, you're going to get a strong whiff of hydrogen chloride gas, which is going to cause a lot of irritation to your tissue. And so watch out for the 12 molar HCl. We usually do this in the hood. 6 molar ammonia. Dilute ammonia has a nasty odor to it. It's got that strong, powerful ammonia smell. But 15 molar is much, you've already used 15 molar, but just be careful with that stuff. 6 molar nitric, so we're using dilute and concentrated nitric. Concentrated nitric, you got to watch out. That's a powerful what? It's a powerful acid, and it's a powerful. Well, the powerful acid is going to cause burns, but this one is going to cause. It's not flammable. It could cause things to. Is oxygen flammable? Oxygen is not flammable, but oxygen you need to support combustion, right? Because it's an oxidizer and you need a reducer. Oxygen is what we call what? An oxidizer. What's nitric acid?
A reducer.
No. Another oxidizer. You guys remember this at all? We talked about this quite a lot, in the first and the second week of class. Do you remember anything from the oxidizer and reducer thing? No. And so it's a powerful oxidizer. Nitric acid is what we call an oxidizing acid versus hydrochloric acid. Hydrochloric acid is also an oxidizer. Hydrochloric acid can oxidize lots of things, lots of metals. It eats it up, like magnesium, zinc, etc. But nitric acid will eat up a lot more things because it's significantly more powerful of an oxidizer. Yeah, don't forget about the earlier stuff. And the best way to remember the earlier stuff is to go back, because usually you got to think, like if you're a UCLA, UCLA is on the quarter system. It's only 10 weeks long. You don't have much time, to prepare for the final, because in 10 weeks you got the final. We're week 7, so it'd be like 3 weeks to the final exam. And then you have this stuff memorized. Well, it's not all memorization, but there's a lot of memorization. This is one of the things that people find very difficult about organic chemistry. Organic chemistry is a lot of memorization because of the nomenclature. It's like learning a new language. And so if you're good at learning new languages, organic might be okay, not so bad, because you learn a lot of jargon. That's what I found a lot of people struggled with in organic, was learning all the nomenclature, naming things, and memorizing all that, and then memorizing reactions. But it's not just memorizing reactions. Initially, it's memorizing reactions, but then you see patterns. Once you see the patterns, then you don't have to memorize anymore. There's certain patterns of reactivity. And so, anyway, you want to go back through and just review the stuff so you can recall it. And then ammonium chloride's no big deal. 3% hydrogen peroxide is household hydrogen peroxide. This is potassium hexacyanoferrate 3, but this, or ferrate 2, this ferrate 2. This is not so hazardous. Use that. Even though it has cyanide in it, the cyanide ligands are strongly bound to iron. And so it's not like free cyanide. If this were potassium cyanide, then it'd be pretty hazardous. There's something called aluminum reagent, which is a dye, 1% dimethylglycine. These you'll find in the little dropper bottles on the ends over there. Barium chloride. Barium is what we call a heavy metal. It's a group 2, but it's bigger. Ammonium oxalate. Oxalate causes like kidney stones. So you don't want to eat this stuff. You don't want to eat this. You don't want to eat that. Although, they give barium cocktails. When you go for a CAT scan, they give barium cocktails. But the barium cocktails they give is a suspension of barium sulfate. Barium sulfate's not soluble. And so the barium chloride's highly soluble.
So you get higher contrast.
Right. Since a heavy metal has a lot of electrons, and it's good at absorbing X-rays, like lead. Lead is great at absorbing X-rays, but you don't want to take a lead cocktail, even if it's lead sulfate, because of heavy metal poisoning. And so barium is a lot less toxic than lead, but still it's a heavy metal. So you got to be careful. The barium chloride I don't really worry about so much. I've had barium sulfate cocktails a number of times and survived. Magnesium reagent is another dye. Iron 2 sulfate. Iron 2 sulfate is green. Iron 3 is yellow. And if our green iron 2 sulfate turns yellow, then it's gone bad. It's just been oxidized. And so we know that this one you leave the cap on, so it stays fresh longer. Otherwise, the shelf life of iron 2 sulfate is not very long. It'll be oxidized by air pretty easily from iron 2 to iron 3. This is stabilized with iron wire and 0.01 molar H2SO4. The iron wire, because iron 2 is a reducing agent and oxygen is an oxidizing agent. And so if we have a reducing agent that's even better than iron 2, then that's called what we call a sacrificial reducer. In the jargon of electrochemistry, we call that sacrificial reducer the sacrificial anode. And so we have a sacrificial anode, which is the reducer in this case, which will be the iron wire and H+. So this will hopefully keep it stabilized longer, but ours is not. When you look in our green bottle, there's no iron wire or sulfuric acid present. Sodium chloride is generally regarded as safe. Generally regarded as safe as GRAS, grass. Chlorine water. Chlorine's a powerful oxidizer. This is yellow, green water. Mineral oil. Mineral oil is used for lots of different things. I don't know. Yeah, I think I know what we're using them for. Mineral oil is the mineral oil we use is used to dissolve non-polar substances. And so we could use the mineral oil to dissolve non-polar things like iodine and bromine and that type of stuff. Barium hydroxide, I don't know what we're using that for. Solid sodium sulfate, sodium nitrate, sodium carbonate, sodium chloride, sodium bromide, sodium iodide. I think we're going to skip some of the solid analysis. And then these 0.1 molar solutions of all nitrate salts. Why nitrate? Because nitrates are all soluble. So ammonium, silver, iron 3, chromium 3, aluminum 3, calcium 2. Well, calcium is always 2. Sodium, zinc. Zinc's always 2. Nickel. Nickel can be 2 or 3. Nickel 2. Magnesium. These are the known. So these cations we're analyzing. What anions are we analyzing for? We're analyzing for nitrate, sulfate, chloride. What else? Bromide, iodide. Wow, that's a lot. So how many cations are we analyzing for? Sodium, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 cations. 1, 2, 3, 4, 5, 6. 6 anions. Some of these anions are incompatible. So for example, if we had silver present, we can't have chloride, bromide, and iodide. Otherwise we get a precipitate in the solution. And so there's some compatibility problems. If we had carbonate, we're not going to have calcium and magnesium, that's for sure, or chromium, aluminum, nickel, zinc. So limits. So we could just do it based on chemical reactivity. We can eliminate a lot of possibilities. So here's our introduction to qualitative analysis. This is how I prep my notebook. How I prep my notebook is I just draw the flow chart in the notebook here. And then we go, well, what are the amounts? Well, we need to know how much initial solution we need to start with. And so let's see how much initial solution I need here. So the first part of the talks about the reaction. And then we get down to the procedure here. All right, so we're going to do initial observations and tests for sodium and ammonium. Note the color of your sample and record any conclusions about what cations are present or absent on your report sheet. So you look at the color. Is it colorless? If it's colorless, then you can eliminate some potentially. You know, if it's got color, then you might be able to tell what species are present. Okay, we're going to do the flame test for sodium, which I'll talk about later, maybe now. Maybe I'll talk about it now. The flame test for sodium is very sensitive, and traces of sodium ion will impart a characteristic yellow color to the flame. Just about every solution has a trace of sodium, and this will give a positive result. In other words, sodium is ubiquitous, and it's so easy to contaminate anything with sodium. Anything you touch, you leave a sodium residue. Did you know that? So if I were to touch the wire with my finger, I'm going to test positive for sodium. Why? Because, your perspiration is going to have sodium on your skin. Everything has sodium, including glass. Sodium can leach out of glass. So normally when I was testing for sodium, for very sensitive tests, I wouldn't use glass. I only use plastic. So I use plastic beakers, plastic everything, because glass can contaminate things with sodium. Not much, I mean, just very little, but still enough to detect. Sodium is very easy to test positive for, but you know that ease of testing positive for means it's easy to get a false positive. Do you know what a false positive is? A false positive means you tested positive, but you don't really have it because somehow you contaminated it and you tested positive in that sense. And so the flame test I don't like to do. I like to do this when there's time. Like say something's cooking, then I'll do the flame test. And so what I like to do is I like to start other parts of the procedure because the flame test is very quick, except cleaning this is a pain. It depends on how much contamination you have on the wire. And so what we use is we use like a platinum. Oh, that's a huge flame. We use platinum or some other chemically resistant or unreactive wire. So you want to get a nice little cone like this. And the first thing is you test your wire to see if it imparts a color to the flame. Do you see that yellow color? I just tested positive for sodium here. But what I want to do is, okay, I'm going to do either two things. And this, I like to do this in the hood because I don't know who used this last and what ions. You know, if there's, let's say, if there's some silver or lead on this, I don't want to breathe in the vapors of silver and lead. So I like to do this in the hood and then just burn this off. This, I think, is just sodium. So I think we're going to be all right. Okay, that's number one. Number two, this is your known sample, so it has all these ions in it. What ions does it have that you don't want to breathe in? Scroll up. Well, I don't really want to breathe in silver. Silver is a heavy metal. I don't want to breathe that in. Maybe iron's okay. Aluminum, I'm not going to worry too much. Chromium, I don't want to breathe that in. Nickel, I'd rather not. You know, actually, I'd rather not breathe any of these in, you know, if I can avoid that. And so what I'm going to do is I'm going to do this in the hood. But just to demonstrate this, let's just do this. So what we're going to do, the first part is we're going to clean the wire. Now, how do we clean this wire? We need to clean this wire by, we're going to dip this into a test tube of concentrated hydrochloric acid. And so you get a test tube of concentrated hydrochloric acid, dip this, then burn it. Dip it and burn it. Dip it and burn it until it comes out clean. Then we can run a test. Like, for example, let's test tap water for sodium ion. We test it. Well, I just tested positive, but do you see how much more intense that is? So tap water will test positive for sodium ions. When you dip this, be careful. If you get the glass hot, don't quench it because it'll just crack and fracture. And so what you need to do is you just need to get the wire hot, and then dip the wire, but don't dip the glass part because we don't want to thermal shock that. And every semester somebody does thermal shock it. So essentially you just need to clean this and then you'll dip it in your solution and then look for a bright yellow color like what we saw with the tap water. Okay? It takes time. So I wouldn't start with the sodium. You can do the sodium at any time. We can also do the ammonia test at any time as well. This preliminary examination, color, flame, and ammonium, the ammonium test and the sodium test are independent of this flow chart. So what we're going to do is we're going to do the ammonium test and the sodium test when there's a break, in the procedure or whatever, and we have time. Instead, we're going to go straight to number 2 here. We're going to use HCl, and what we're going to do is we're going to try to precipitate out all the silver chloride. And so what do I need as far as notebook prep goes? I need to know how much solution I should start with. And so I'm going to scroll down here to the procedure and go to number 2.
So what have you do we write for number 1? Just the,
What do you write for number 1? Nothing right now. Just start at number 2.
left side just starts with number 2.
Well, unless, did you already prep? Did anybody already prep? Yeah? No?
He told us not to.
Yeah, just to make sure. Yeah, for number 1, we're going to do it when there's time. So what you could do is you could, you're going to insert it somewhere here. We could do it now, but what we want to do is we want to get started on the more lengthy part of the procedure, and then we'll worry about that later. So sodium and ammonium, just save it for the end. What you don't want to do is you don't want to run out of time on the lengthy flow chart. You could do sodium and ammonium are quick tests. It's not so quick, actually. It's quick if your wire is clean, but all your wires are going to be dirty. And it's going to take you like 30 minutes to clean it. Something like that. Some people more, some people less. Some people have spent 40 minutes cleaning, 45 minutes cleaning the wire.
So it's not short.
But once it's clean, then it's short. It doesn't take any time. It's a really easy test. Did you see that, how quick that was? So easy. You could do the same thing. If it's very light, then you can dip it and then see, does it really brighten it up? The ammonium test is very short also. A lot of you have already done the ammonium test, well, not a lot of you, because I guess you didn't have lab, did you? If you had Chem 4 here, then you've done the ammonium test before.
That was, for me, that was 3 years ago now.
Yeah. So we'll talk about the ammonium test and the sodium test later. We're going to get into the flow chart now. And so just start at number 2. Number 2 now, place 10 drops. 10 drops is about how many milliliters? 20 drops is about 1 milliliter. So 10 drops would be about half a milliliter. So there's 2 things that you're weighing here. Because you don't have to follow this exactly. In fact, we aren't going to follow it exactly. The 2 things are, 1, more volume means it's going to be easier to detect, because by the end of this, the 10 drops you start off with at the beginning of the flow chart, and if you are not adjusting things as we're going along, that is, if you follow the procedure as written, you're going to have problems at the end. The problem that you're going to have at the end is it's all disappeared. There's nothing left. So you're doing your known, and you have all those cations here, but by the time you're here, you're getting all negatives. And you're getting all negatives because you lost it all already. And you have to be very careful in how you do this. And so on the one hand, I'd like to use 20 drops or 30 drops or 40 drops. If you use 40 drops, then by the end, most likely, if you lose a bunch of it, no big deal because you still have enough to test for. But on the other hand, if you start using 40 drops, you're going to run out of room in your test tube. And then you're going to have to switch to beakers and then bigger beakers. And then beakers don't fit in the centrifuge. So you're going to have to do multiple centrifugations, which is going to be a pain. And so what we have to do is we're going to use 10 drops of our unknown, and then we're going to have to change how we do the procedure. You cannot cookbook this so well. You could cookbook this if everything were written, perfectly for your sample, but it's not. This is just a general one-size-fits-all. Like if you go and buy a one-size-fits-all pair of pants, are they going to fit you properly? No. And so the same thing here. A lot of people think, okay, I'm going to do this one-size-fits-all procedure and expect it to work perfectly. It doesn't. And so what we're going to do is we're going to start off with 10 drops, or a little bit more if you want. Just a little bit more, not too much more, because then we're going to exceed the capacity of our test tube. And then we're going to be very careful how much of the other stuff we add. And so, for example, how much HCl do I add? Well, if you read the procedure, the HCl is one size fits all. If it's one size fits all, they're going to get the biggest size and make everybody wear that, right? And so this is how come people, when they get to the end, they're following the procedure. They said, I followed the procedure exactly. Well, unfortunately, it didn't quite work out so well for you.
Why don't they change the procedure then?
Well, okay, I'll get everybody's small pants. Everybody has an unknown. Everybody's unknown is not the same. If everybody's unknown was the same, then yeah, that would work. But since everybody's unknown is different, it doesn't work. And so what we need to do is we need to do it starting with the known. How to do this with the known. All right, so the way we're going to do this with the known is like this. We'll take our known solution here. It's only 10 drops. And then I'm going to add the HCl. Now, how much HCl do I need to add? Okay, so when we add the HCl, this is what we do here. We add it drop by drop. Now, I need to know what molarity. Am I going to use the 6 molar or the 12 molar HCl? So I need to know the molarity of the HCl I want to use. And so that we have to write down. Some things have dilute and concentrated, especially acid. And so in this case, we're going to add the 6 molar HCl. And then we have dilute and concentrated ammonia. And so in this procedure, we're also using the 6 molar ammonia. And we're going to use the 6 molar nitric acid. There's a caution here. Caution, nitric acid can cause severe burns. Avoid contact with it. If you come in contact with it, immediately wash the area with copious amounts of water. What about HCl? HCl does cause burns, but not as severe as nitric acid. Nitric acid is an oxidizing acid. A pretty white precipitate of silver chloride confirms the existence of silver on it.
You dissolve like a paper towel with the hydrochloric acid through sulfuric acid for us. I like to see that.
Yeah, with sulfuric acid is also an oxidizing acid. And so it can cause that.
Watching acids dissolve.
I'm sorry?
Watching acids dissolve things is fun.
Yeah. Yeah. Nitric acid starts to fume, do all kinds of stuff. So it's pretty cool. So here, I just write 6 molar HCl. Here I'd write 10 drops. There. Here I just write 6 molar ammonia. Here I write 6 molar nitric. We're using 6 molar of all these, the dilute. And then I'll just have the flow chart like this. Now, how much HCl do I add? I don't pay any attention to what the procedure says. Oh, I add as much as needed, and that's it. I don't add too much, and I don't add too little. How do you know how much is just the right amount? How do you know you have just the right amount? We're going to do this for all precipitations. For all precipitations, and there are a bunch of precipitations here. Every time we do a precipitate, you see on the precipitate forms a solid box, and this says precipitate here. Here's another precipitation. Here's another precipitation here. So whenever we do a precipitation, we'll have this drop by drop here. And what's going to happen is the solution is going to get really cloudy with precipitate. It's going to get so cloudy, you can't tell if you're forming more precipitate or that's it. Right? What's going to happen is it's going to cloud. What you're looking at is you want to keep adding it, and if it continues to form more cloudy precipitate, you keep adding it until it stops. But it's hard to see. When it becomes too hard to see, what we do is we stop adding it, and then we take it to the centrifuge. Here. And so there's a centrifuge over here. Let me just grab that. You put it in the centrifuge here, close the lid, and then turn the dial. And then listen to it. Boy, that centrifuge is quiet. Once it's reached maximum RPM, then we'll turn off the dial, and then we can slow this. You can get a piece of paper towel, or just slow it by gently applying friction to the black ring here. You don't want it to come to an abrupt stop. Just let it come to a gentle stop here. Then remove your sample. So after we centrifuge it, what's going to happen is that's going to compact the precipitate down here. And then what we end up with is a clear solution up here. And then what we'll do is we'll continue adding HCl. As we continue adding HCl here, we're looking for additional cloud formation, so we'll just add 1 drop. If we add 1 drop, and we have more precipitate, then we're going to keep adding. We're going to keep adding, and keep adding until it stops precipitating or we can't tell. And so let's say it clouds up again. If it clouds up, we haven't added enough. And so then what we're going to do is we're going to repeat this until when we add 1 drop, no precipitate forms. And so with 1 drop of HCl, we get no precipitation. Then you know you've added just the right amount. Not too much, not too little. This goes for every single precipitation that we do. So for every single precipitation that we do, I don't write the amounts. I adjust the amount until it's perfect. Does that make sense? You want it perfect.
You have to balance the centrifuge.
Yes, you have to counterbalance the centrifuge. So what you're going to do is you're going to take one test tube. Let's say you don't want something this full, and then fill a blank. That is, fill an empty test tube the same height with just water, DI water, and that'll balance it. Otherwise, it's going to start rocking, and you'll hear it too. It's going to make a lot of noise. It'll be really fussy. Okay, so we got the precipitate here, which is the white precipitate. I wish they would have done this with the boxes. Now, what happens here is this precipitate should consist of silver chloride, and then all the other ions should be in the solution, all other ions. So what we need to do is we need to separate them. And the way we separate this, there are two techniques that are commonly used. One technique is just to decant it, but if your precipitate isn't well compact, then decanting it could lead to some precipitate flowing over. The other technique is to pipette it. So you get a plastic pipette, one of the long ones. Let me see if I have one here. The medicine dropper doesn't work very well, but we should have some plastic. Actually, this one would work. We should have some plastic pipettes as well. So you're either going to decant it, which just means pouring it off, or you're going to pipette it out. There's two options, depending on how well compact that precipitate is. And the situation is we don't want to lose any of this, because this contains all other ions. The more of this we lose, the less we'll have at the end. And so what we want to do is we want to make sure we transfer all of this over to here. This is the remaining ions over here. And so we're going to decant and try to get those. But we're not going to be able to get all the liquid off. When we decant this, there's going to be some residual liquid here, and then this precipitate is going to be coated with this solution that contains all the other ions. And so what we're going to do is we're going to wash this here. And so let's talk about the washing step. What I want to do is I want to make sure I get all the ions over here, and that's going to involve this. So you put in the first wash. Now, how much do you need to wash? Well, you kind of estimate, about how much you would need to wash this with. But to give an idea, let's see how much they say to wash with. You don't want to use too much, and then you don't want to use too little. They're saying to wash the precipitate with 10 drops of distilled water, centrifuge, and add the washings to the decantate. Okay, so the first wash, we'll just add 10 drops, max. Okay, when we wash this, we'll probably suspend the precipitate here, like this. And then we're going to centrifuge. And add decantate. Decantate would be the liquid to remaining solution. So the first wash is going to consist of 10 drops. Centrifuge, decant, and combine the wash. Go back here. All right, that's going to capture most of the remaining ions over here, but I don't stop at a first wash. Because if there's any residual contamination over here, let's say I didn't give a thorough enough washing, and some of the ions from over here are still remaining with the precipitate over here, that's going to screw up these results. It's called interfering species. We don't want any interfering species in these remaining tests. So I don't stop at one wash here. I do, because the washes don't take very much time. And so the first wash is this. And then what I'll do is I'll do a second wash. And maybe third wash. Here I could use more than 10 drops because you know what I'm going to do with it, the wash? I'm going to discard it. And so second, maybe third wash, centrifuge, and discard the wash. We don't want to add, even though there might be trace amounts of ions in here, we don't want to add that over there because it's going to dilute it too much. And if it's too dilute, it's hard to detect. The more concentrated the ions are, the easier they are to detect. And so second, maybe third wash, okay, discard, second, and third wash. Washings, I'll call it. Okay, and so what that means is this precipitate has been thoroughly washed. The precipitate has been thoroughly washed, so we'll get clean results here. What happens is every semester somebody comes up to me and they get some kind of black precipitate here, and they're thinking, what's this black precipitate? Why am I getting black precipitate here? Well, it's because you didn't wash it well enough. Some ions got contaminated in here, and they're giving you some bizarre results over here. And so we need to wash this. That goes for all these precipitates. So this precipitate, first wash goes with the decantate, the solution. The second, third wash will be discarded. Yeah. This precipitate, same thing. Also, when we do the precipitate, we do this. We add until it stops precipitating. How do we know when it stops? Centrifuge test. That's how we know when we're done. And so I don't, like I said, I don't put the amounts, but once I know the amounts, like say, for example, once I know approximately how many drops of HCl it takes, I'll write down how many drops. That way, in the future, I know about how much I need to add. Does that make sense there? Okay. Now, once I have clean white precipitate here, I'm going to add 6 molar ammonia. And so what's going to happen here is we're going to go from the white silver chloride solid to this. What's this called?
Not sure which one.
Yeah. Diamine silver 1 ion. This is aqueous. So what we're going to do is how much ammonia do you add? How much ammonia you add is you add the minimum amount of ammonia to dissolve your silver chloride. And so what we do is add a drop, and then this one, when we're trying to dissolve a precipitate, we use a stir rod. We use a stir rod, and we don't do this flicking because it's not enough. You need some mechanical action to dissolve solids. It's like trying to dissolve sugar cubes. If you can break up the sugar cubes, they'll dissolve faster. And so the same thing goes with this. What we do is we get a stir rod in there, and we try to crush up the crystals here with ammonia to get them to all dissolve. We don't want to add too much ammonia. If you add too much ammonia, it makes it more difficult because we're going to have to reverse that later. And so we're going to add the minimum amount of this to dissolve all our solid. Okay, this one they're asking for 6 molar. Usually we use the concentrated ammonia for this, but in the procedure they're asking for 6. The reason the reason why? The reason why they're asking you to do 6 molar is because they don't want you to overshoot it too much. If you overshoot it with the 16 molar, then that's reversing it, and you're going to be reversing it probably in a beaker because you're going to have to be adding so much acid to kill off all that extra ammonia that you added in there. So the 6 molar is easier to control, but not as effective because you have to use a lot more of the 6 molar versus the 15 molar or 16 molar. So anyway, we're going to dissolve all this. How many drops? Well, however many drops it takes. That's how much you should add. However many drops it takes. You don't want to overkill this because this is base. And then after this, what are we going to do? We're going to add acid. And the purpose of the acid here is to destroy the base, the ammonia. And in other words, we're going to do Le Chatelet shift back over to get the precipitate again. So every semester, somebody's successful at getting white precipitate. They get the white precipitate to dissolve, but they're unsuccessful at getting it to reprecipitate. We need it to reprecipitate here by reversing it. We reverse the reaction by adding ammonia, which destroys by adding nitric acid, which destroys the ammonia, which can reverse this previous reaction here. We'll go through the reactions later. What we're looking at is just the technique now. Okay, now once we're here, then it's a positive test. Why did we have to do this extra? Why didn't we just stop here? Why didn't we just stop here? A white precipitate should indicate that we have silver ion. The reason we didn't stop here is because other cations could precipitate with chloride. The other cations would be lead 2 and mercury 1. If there were lead 2 and mercury 1 in our unknown, then we would have gotten white precipitate here. But the lead 2 does not form an amine complex, nor does the mercury 1 form an amine complex. So the only one that forms an amine complex is silver. Why? That's what's observed. That's in the table. If we knew the theory well enough, maybe we could understand why. So this is what we call a confirmatory test. Just because we have a white precipitate here doesn't mean it's definitely silver. It could be other white precipitates that precipitate out with chloride. And so we do this confirmatory test, and only silver does this. And so if we end up with a white precipitate dissolved in ammonia, reprecipitate out with nitric acid, then we're positive we have ammonia. Now, what if we get a negative test? That is, what if we get no precipitate here? If we get no precipitate here, then does that mean we have no silver ion present? It may, but we can't be sure because maybe we overly diluted it. If you overly dilute it, then it's not 100% insoluble. A little bit will dissolve. And so negative tests don't mean much. They just mean either we didn't have it or we missed it. Due to some experimental oversight, we just missed it. A positive test means we have it. And so positive, we have it. And so this would be a positive test for silver. Now for your unknown, the procedure, let me talk about the unknown. Let's say your unknown didn't have any silver ion. And the procedure calls out for adding 20 drops of HCl. After 1 drop, you notice there was no precipitate. 2 drops, there was no precipitate. 3 drops, there was no precipitate. Should you keep adding? No. If you keep adding, you're going to ruin it for the rest of the procedure. So what you'll see is with the first drop, it turns very cloudy. If you're unknown, the first drop, nothing happened, then that's automatically a warning sign that probably should stop adding. So this is what I mean by you can't follow the procedure. The procedure is one size fits all. And if everybody didn't have silver, then it'd be easy. Don't add any HCl, right? Does that make sense? Nate, too? Does that make sense? Why we aren't going to follow the procedure as written? Yes. Yeah, okay. Yeah, we can't because it doesn't always work. Okay, so once we get this silver, then we're going to take care of, we never throw anything away. Okay, we're at the end of the line for the silver chloride precipitate, so we could throw away that, discard it. But for the remaining solution, we never discard that. So don't discard anything unless the flow chart ends there. And so the next step here is we're going to add some ammonia and ammonium. Ammonia and ammonium, what the heck is that for? Well, that's for adjusting it. Here, we have a lot of acid here. And so if we have a lot of acid here, it depends on how much acid we have. If we have a lot of excess acid, then we have to add a lot of ammonia. If we have a little bit of excess acid, then we add just a little bit of ammonia. And so what we're going to do with this one is we're going to add the ammonia until we neutralize the acid. Well, how much ammonia does that take? How do I know when I've neutralized the acid, the HCl? Depends on how much extra HCl I had in there. Well, that could mean a lot of ammonia if you have a lot of HCl, or it could just mean barely any. And so this is how we're going to do this one. Okay, to the decantate, which is the solution from procedure 2, which contains all the other cations, add 2 drops of ammonium chloride solution and 6 molar ammonia until the solution is basic to litmus. So 2 drops, that's fine. We'll add the 2 drops of ammonium. And then we're going to add 6 molar. Well, they don't tell us how much. Well, you're going to keep adding the 6 molar ammonia until it turns red litmus blue. So right now, red litmus is going to stay red. Okay, then we just keep adding it until, it turns blue. Once it turns blue, then we're going to stop. Centrifuge and reserve the decantate for procedure 4. Wash the precipitate with 10 drops of distilled water. Centrifuge and add the washings to the decantate. So in this case, this is kind of a what we call a selective precipitation. Normally, when we do a precipitation, we want to max it out. We just keep adding until we max it out. In this one, we could do the same thing. We can add a little bit more than what's called for here. So here we're going to add the ammonia. To this, actually the ammonium chloride and then the ammonium. What we want to happen is we want to precipitate out the +3 cations. Iron 3, chromium 3, aluminum 3 is the hydroxides. The ammonia hydrolyzes water to form a little bit of hydroxide. That little bit of hydroxide will precipitate up to +3. If we add a lot of hydroxide, then what we're going to get are the +2 cations precipitating as well. And so here, keep an eye on this, because even if we add excess ammonia, it should be fine. But the situation with these +3 is the +3 are so insoluble as hydroxides, it doesn't take much hydroxide to precipitate all of those. Whereas the calcium here, and what else do we have left over? Magnesium, nickel, zinc. These +2 cations, it takes a lot more hydroxide to precipitate out. So here we're precipitating out the hydroxides here. You can see magnesium hydroxide and nickel hydroxide. But in this case, we're using precipitating agent sodium hydroxide. Over here, we're using precipitating agent ammonia. The reason we're not just adding hydroxide here is if we just add hydroxide here, it produces too much hydroxide. Whereas ammonia produces very little because it's a base. Bases have a Kb. They hydrolyze water to form a little bit of hydroxide. The Kb of ammonia is 1.8 times 10 to the minus 5, which is going to produce enough hydroxide to precipitate this out. Versus if we look at this, sodium hydroxide, which is 0.1 molar, would be a pH 14, we precipitate out these hydroxides as well. So this is just to control how much, in other words, this is a selective precipitation. We're controlling precipitating out the +3 hydroxides versus the +2 hydroxide. We want the +2 hydroxides to stay. Even if we add excess ammonia here, it's not going to be too big of a deal because these, well, actually magnesium, if you have way too much ammonia, then you can precipitate out the magnesium. So we might lose the magnesium over here. So we'll just stop here when it turns blue and then maybe add a drop additional, see what happens, or a couple of drops additional. Okay, is that clear for this? Or not at all? Are you guys still following? No? Kinda. All right, so this precipitation is a bit tricky because this is what we call selective precipitation. The selective precipitation is precipitating out the +3 and leaving the +2 in solution. And so we have to use the right amount of hydroxide. The right amount of hydroxide is, later on we can calculate the pH at which these precipitate. So at about a pH of 7, all of these should have been precipitated out. But anyway, we'll go to blue here, just follow the procedure in that case. And then we precipitate out these 3. Then what we'll do is we'll wash, and then the first wash gets combined with the remaining cations or the decantate. The second and the third wash are thrown away. Yeah. This one will probably just one wash. And, okay, now once we have these 3 precipitates or however many you have, then what we're going to do is we're going to add sodium hydroxide. And this one we're going to add excess sodium hydroxide. The excess sodium hydroxide will attack aluminum. Aluminum likes to form the tetrahydroxyl complex. There's a tetrahydroxyl ion. And so the aluminum will dissolve in sodium hydroxide. The iron and the chromium will not. Okay, but this is chromium 3. And so what we're going to do is we're going to add hydrogen peroxide to this in the next step. The hydrogen peroxide is going to oxidize chromium 3 to chromium 6 in chromate. Okay, so this one will just follow along the procedure. This one will just make sure we have enough hydrogen peroxide to oxidize that. Iron 3 is already maxed out. Aluminum 3 is maxed out, so we can add excess hydrogen peroxide, make sure we get rid of all the gray green precipitate. If there's any gray green precipitate remaining, then you haven't added enough. We've got to get rid of that, and then that's going to convert it to like this orange, yellow solution here. Okay. Okay, that's going to leave us with iron 3. Again, we're going to wash this. The first wash goes over here. Second wash, discard. Third wash, discard. And then iron 3 hydroxide is a precipitate. We're going to dissolve this in a minimum of HCl. That dissolves iron 3, and then we're going to precipitate it with a new precipitating agent here. The new precipitating agent would be this. This is going to be the hexacyanoferrate ion, ferrate 2. And the hexacyanoferrate 2 is going to precipitate this and make a blue precipitate here. This blue precipitate is a very famous one. You'll probably take a look at the color of that and see what it looks like. Okay, to the decantate here, which is going to consist of aluminum and chromium, we're going to heat to remove the hydrogen peroxide. We don't want hydrogen peroxide there and ammonia. Hydrogen peroxide is an oxidizer, ammonia is a reducer. So we don't want any reaction occurring between that. So we're going to boil off the hydrogen peroxide or heat it. Then we're going to add HCl. The HCl is going to destroy the complex here, create aluminum ions. It's not going to do anything. Actually, it is. It's going to convert chromate to dichromate. So this is going to go from kind of a yellow to an orange color here. And so we get this acidic. You can tell it's acidic because of the color change. You can't tell based on the aluminum, but you can tell based on the color change of chromate to dichromate. One's enough. You don't want to add too much HCl because in the next step we got to add ammonia. Ammonia needs to do something, but the first thing it's going to do is it's going to neutralize the HCl. Once the HCl is neutralized, then it can attack what? Well, the ammonia is going to precipitate out the aluminum again. So we're just going to use ammonia to precipitate out the aluminum. In this case, we're not adding any ammonium. The ammonium was to help control the precipitation earlier and not generate too much hydroxide. Here we don't care. We can have lots of hydroxide because the dichromate is not going to do anything like that. And so the ammonium will precipitate out aluminum. This is a very light precipitate. That is, it's not very dense. And so this is hard to centrifuge. And so what it looks like is it looks like Jello. And what we're going to do is we're going to take this gelatinous precipitate and dissolve it with HCl, a minimum of HCl. And then what we're going to do is we're going to add aluminum, which is a dye. So we'll add a drop of aluminum and then reprecipitate it with ammonia. And so this is like adding red food color to Jello. It's going to take clear Jello, clear colorless Jello or white Jello, and make it red. And so what we're going to do is we're going to get red Jello. And the red Jello, we're going to centrifuge, and that's going to compact the Jello on the bottom. And when we look at it, it looks like a red lake stuck at the bottom of the test tube. That's what it is going to look like. And this is what they call the red lake test, because we're going to generate this red Jello, which when centrifuge forms a little lake at the bottom of the test tube, and then you have this clear solution above it. Now, chromate and dichromate's interesting. It's chromate in basic solution and dichromate in acidic solution. pH changes which form we have. Both of these are chromium 6, and so they interconvert from one another. So we're at dichromate, which is orange, in acid. Then we hit the base in there, and then it switches into yellow chromate. Well, with the yellow chromate, we're going to add barium and form a yellow precipitate, barium chromate. So this would be the positive test for barium chromate. And so I'll just talk about this branch for right now, and then we'll stop here. And so again, we're going to do the flame and the ammonium test later. Today, we'll just start on this branch and see how we're going and see how far we can get. So you can work independently or you can work with a partner for this. Okay, are there any questions on this? Uh-huh.
This is a multi-day lab, right?
Yeah.
Where are we just saving all of the precipitate?
Solutions in your drawer. Right.
Where's the known?
No, the known, let's see. Checked it earlier. We might have to get the known from the stock room. So if we get the known from the stock room, then they're going to ask me to bring they put some other stuff here. They put some pipettes here. They put some stir rods here and some paraffin here. Just keeping stuff in your drawer. Usually they put the anion unknown out. They didn't put the anion unknown out. The cation unknown you have to get from the stock room. When you go to the stock room, you bring a small beaker or the cation unknown, a clean beaker, and they'll put some known solution in there for you. Okay.
It's separate?
I'm sorry?
It's separate?
It's separate.
So we would theoretically do this whole thing twice?
No.
No.
For the known, you're going to go through all the cations here, and then you're going to take a second sample, which is actually a totally different sample. It's the anion unknown, or the known. The anion known, because of incompatibilities, we can't have them both the same. And so you'll have a separate sample. The anion known contains sodium salts of all these. Sodium salts are all soluble. And so if you were to test your anion known solution for cation, you'd only test positive for sodium. There are no other anions in there. And that way we can have a mixture containing all of these. And then we'll test all these. But we'll do the anion test after, because the anion tests are individual tests.
Okay, so it's a different like.
Yeah, it's a totally different flow chart
Okay.
for the anion, and it's separate flow charts for each one. So sulfate has its own, nitrate has its own, etc. It's a long procedure. So you'll just try to get as far as you can each day, basically, and then still have enough time. So we're not going to analyze them side by side. We're just going to do the knowns first, see what you're supposed to get, and then run your unknown after that. The unknown's worth points there, so you want to make sure you do a good job with identification of the cations and identification of the anions in that sample. All right, so yeah, bring a small sample. I mean, no, a small beaker. Tell them. Let me see if they have enough wire so that you can keep it in your drawer, so you don't have to clean it more than once.